Okay, so welcome everyone. This talk is about, as it suggests, the state of deep learning. It's an introduction to deep learning, so if you have worked with deep learning algorithms and techniques before, probably majority of the talk will be a repetition for you. Nevertheless, I tried to make it kind of like interesting, and even if you have heard about them before, you can still maybe sip on your coffee, or you don't have coffee, whatever. And just enjoy your time, okay? And the idea here is that this is not like a standard talk. I want it to be interactive. So at every point during the talk, if you have a question, just raise your hand and stop me. I will see if you guys have any questions. So let's start. Let me start by introducing myself before I go over the talk. I'm Ehsan Kamalinejad. My students and sometimes also my colleagues like to call me Dr. K, which is fine with me and it sounds cool, so I like it. So, and my specialty, well, when I was doing my PhD, I was doing a combination of differential equation and nonlinear optimization. Nonlinear optimization in particular is very related to the techniques in general in machine learning and in particular deep learning. So that was my point of entry to this subject. After I finished my PhD, I was working with a few colleagues in the LA area with a few people in UCLA and UCR, and I was that was the starting point for me to get serious about deep learning. I had a little bit of idea about generally machine learning and deep learning because I did my PhD in University of Toronto, where was the birthplace of deep learning. So even before I get serious about it, I knew a little bit about it. So that's about me. Okay, so let's get to work and let's start. So this is the logistics of the talk. I have divided into 3 pieces. The first one, we're gonna just basically, it's an introduction to what deep learning is. Why does it matter? What's the importance of it? And maybe just talk a little bit about the theory behind it. And in the second part of the talk, for those of you who are interested to know about how you might want to enter the field, I will give you a little bit of guidance on that. And then finally, I'm going to finish with a toy example. Initially, I wanted to make the toy example a hands-on experience that you also code with me, but then I realized that it needs some more extended time, that for just a demo, it needs maybe 1 hour to go over it. So I'm going to show you what is going to, so I'm going to show you the code, but we're not going to go over the implementation together. Okay, so that's the logistics of the talk. Let's start. So what is deep learning? Well, first of all, deep learning is a sub-branch of machine learning. And machine learning, so what is machine learning now? So machine learning is a bunch of techniques that you allow an algorithm, a machine, to learn from experience without being explicitly programmed to do so. So I believe that the best way to distinguish between a machine learning algorithm and a usual standard, like traditional algorithm, is to go over an example. Think about tic-tac-toe, okay? A simple game of tic-tac-toe. You can, if you want, you can write down and sit down and write down a bunch of rules. That these rules will they will explain that how the computer should approach the problem. So if the computer follows that rules, most probably it's going to be a winning strategy. So you're going to go over the logic of how the winning strategy works. and you dictate that logic to the computer, and the computer will follow that, and it will, if your logic and your strategy is good enough, the computer will always win, right? So that's like the traditional way of approaching problems using programming. And I call it design algorithm. Okay, so you design the whole algorithm to do something. As opposed to that is the machine learning approach. The machine learning algorithm, in a machine learning algorithm, you don't really tell the computer what the winning strategy is. You just show the computer, in fact, in this scenario, probably you're going to let the computer to play with itself. Many games. And you attach it to a neural network that I will explain what it is in a bit. And it will learn the different states of the game. After playing, for example, for this particular setup, it says that after 40,000 games, it will learn how to play the game, right? Note that there is a significant difference between this and the traditional algorithm approach. You're not telling the computer what the winning strategy is. It will learn on its own. And it's a completely new paradigm. I think the most important thing about machine learning in general and deep learning is not the specific techniques that got popular in the last few years. But the most important thing is that for a computer, if it has an algorithm, if it has enough parameters that are interacting with each other, which I call them like learner parameters, you can teach it the same way that you teach a 5 years old kid to do something. It's very different than the design algorithm that you go over the strategy of doing something, right? You just show the computer as opposed to, you show it how something is done as opposed to tell it exactly what is the process of doing something, right? So there's a significant difference between these two. And so that is that led to this new paradigm of algorithms that are very powerful and very different, in fact, than the algorithms that we had before. So, in fact, from many other things that we were doing traditionally, and you feel that most probably there's not going to be a lot teaching method that you can apply to them, you can still use machine learning algorithm. This is a recent example from Google, and they were going over indexing, basically search and stuff like that, which Google is the best at. And they were showing that by using a neural net-based indexing, they can outperform the standard methods by 70% while consuming 90% less memory. So it's more powerful and less hungry for energy and memory and computation. So it's great. Now let me quickly go over the history of deep learning. I don't want to spend that much time on it. There are so many different resources that you can find on the net to go over this, but I want to quickly go over it. I'm not sure if it is even readable from the back of the class, but maybe. So the ideas of AI, artificial intelligence, has been around for quite a while. It's not a new thing. In fact, from the very beginning of computer science, probably some of you are familiar with Alan Turing, right? The father of computer science, people say. And even him had this idea of creating artificial intelligence, right? Well, he couldn't do it, but he started thinking about it in a serious fashion, right? So it goes way back to 1950s or so. And even the newer ideas in machine learning, which we now call deep learning, are not necessarily very new. the first neural networks that people created goes back to 1980s. And at that time, several people were suggesting that if you use these structures, at least theoretically, it seems that you should be able to get good results. However, people could not work it out at that time. So these ideas were around. And in fact, one of the people that we will hear about him again, two of the people that were advertising for this idea are now the leading people of deep learning, like Jeff Hinton and Jan LeCun, also Yoshua Bengio. So these people were saying this from a long time ago, that this thing is going to work. But they couldn't work it out. It was just like a prototype and lab experiment kind of thing that it was supposed to work. Now, three reasons led to this breakthrough that we observed from like 2010 or so. Well, there was the availability of the data, so internet era. There's a lot of information and data available for you to use to train your models, to do whatever, right? Then there is the computational power. Mainly, at least at the beginning, it was GPUs, the processing power units that were mainly designed for video games. And the reason why they work very well with neural nets and deep learning methods is that they are specifically designed to handle vector operations, because all the games, all the 3D games, it's all about vector operations. Every time that in a single, in a first-person shooter, you rotate your character, it's really a matrix rotation that is multiplied to the space. So it's all about matrices and vectors. Now, they are very good in doing that, and neural nets exactly need that kind of operation. So it happens to be the perfect combination. Finally, there were also a few new implementations ideas. The fundamental ideas were there, but there were a few new implementation ideas, such as, for example, ReLU activations and stuff like that, that helped to make these methods more efficient. And they all happened around, I mean, they all got together around 2010. And one of the places that was very active at that time was University of Toronto. So I was hearing, when I was in my PhD, I was hearing all these news that, oh, people are doing amazing things about stuff. And so this led to the deep learning breakthrough. And really, in my view, this is a personal opinion that might not be very accurate. I don't think those three reasons that everyone is talking about is the reason that necessarily that the deep learning got so popular. The main reason I feel that, which is related to that, is that at around 2012, for the first time, people observed that it's actually possible. From like 1980s, people were saying that these things should be possible, but no one had seen a working one before that. So at 2012, something happened that the whole industry and science community got interested. There's this ImageNet competition that people propose their algorithms for a classification task. It's a pretty challenging classification task. There are over 1,000 different classes and around 1 million images, and you are supposed to propose an algorithm that can classify all these images. It's a pretty challenging task. And before the deep learning era, so this purple color is the deep learning era. Before that, the accuracy of these models were around like 25 to 30, and I mean, that's the error rate. So the lower is better. And this is not good. And also, when you want to boost your accuracy, the difficulty of the problem doesn't go up linearly. So if you want to go from 22% to 20%, it seems like a small jump, right? But to do that, man, you probably have to write a PhD thesis, right? And now, all of a sudden, this algorithm came in and blew everyone else away at 2012. So everyone got excited about it. What is going on here, right? The whole vision industry was thinking about it. And that was the Alex Smith that was proposed by Jeff Hinton's team and Alex Krzyzewski and others that got the good results. And you can see that at around 2014, we actually surpassed human level. So right now, in the vision classification task, we have algorithms that are better than you and my vision, right? So that's pretty impressive.
I think the same sort of happened when people started using deep learning in machine language translation.
Yeah, translation is getting a lot better now. And I believe that we are currently at the level that it's comparable with good translators. And I wouldn't be surprised in a few years that we surpass like human translators. That's another example of deep learning. But this one was the first that proved that this idea works. And that was very important, because as soon as you know that something works, then you ask, okay, if it works for such a challenging task, what other things you can do with it? So that was about deep learning. And okay, so something should play here. So why deep learning is important, especially nowadays? I want to go over a few examples. This is the self-driving car algorithms from NVIDIA, and this is I'm just giving you my personal opinion. I believe that they have done the best job in the self-driving, because there are like so many different companies that are doing that, but I believe that NVIDIA is the best in that. Well, of course, you know, we are getting to the level that is comparable with a human driver. I know that some of you are thinking about the recent accident, a fatal accident. Of course, that's an important thing. But if you want to be like not biased against AI, you would think that, so just think about it, how many accidents every day do we have, right? And just how many of them are fatal? I haven't looked at the data, but you can probably do that. And you know that it's not going to be a small number, right? So having like 1 or 2 fatal accidents, it's unfortunate, and we have to think about them. But it's not, statistically, it's not significant, right? Even thinking about the number of cars that that are using self-driving technology. So anyways, so this is one example that deep learning is important, and it's doing something. It's an alternate solution to the existing problem, the commute problem, right? You can solve it using deep learning methods. You can solve it using AI, right? So in near future, I'm expecting that most probably you don't need to drive your car, or probably you don't need to even own a car, and then there will be some other cars that will drive you to your destinations, right? So that's one example, but that's an example of an existing solution, which is we have an alternate solution for it using deep learning. Another one is this one that Google recently published, and this is a problem again that we have a solution for it, and this is the problem about the diseases, the eye diseases. And ophthalmologists can, if you go to an ophthalmologist, you know that they look into your retina, and based on the texture of the retina and many other things, they can detect if your eye has any disease or stuff like that, right? And recently, Google and a few researchers from medical sciences got together and they create this algorithm that can now do the ophthalmologist job. And the interesting thing about it is that the accuracy is higher than an average ophthalmologist. So, I mean, I don't want to be mean, but I mean, a person that has a PhD and has spent several years of his or her life to just detect what images are what, maybe they don't need to do that anymore. Of course, it doesn't mean that they don't need it anymore, right? There are so many other things that an ophthalmologist will do. But this specific task could be replaced with higher accuracy and much less expensive with just an algorithm, right? So this is another example of an alternate solution to an existing problem. And finally, this was quite an interesting problem. Again, an alternate solution to an existing problem. Based on the data that you get, that astronomers gather from Hubble telescope and other telescope on the Earth, they can detect if there is a planet close to a star, right? So they look at the all close by stars and they try to detect whether there is a planet close to them. So these planets could be some opportunity for us for long term in the future, right? We haven't still done it for even Mars, which is very close by. But to just think about the future, maybe some candidates for planet Earth version 2, right? And so what happened was that a group of researchers from Google, and if I'm right, from MIT Astronomy, it was Harvard or MIT, I don't remember right now, and got together and tried to do the same kind of ideas that astronomers do on their own, but do it using machine learning. And they applied it to the data that they have, and not only they managed to do the same kind of task that astronomers were doing, and it's a hard and tedious task. Even astronomers don't like to do that. Not only they could do it automatically, but they also found 2 new planets in the current data that has been around for a few years. So it was already there, but it was hidden underneath so much data that these algorithms could find them. So it's quite an interesting another problem. Now let's switch gears and go to some other directions that are not alternate solutions. These are completely new paths that probably, if they were not, you wouldn't think that they are possible necessarily. What you see here is a generative model. A generative model is a model that it uses some distribution of a given data, and it will try to find new points in the distribution. In this specific case, these are faces of celebrities, okay? And these are fed to the model, and then the model asked to create new faces. Just think about it. It's a very challenging and interesting problem. And this is now generated images. Just look at the quality of these images. This person does not exist, and so does her, and so does him. These people are not real people, but they look very real, right? These are computer-generated faces, and there's no limit to it, right? You can generate as many as you want, right? Just think about the effect that it has, in entertainment industry. Those scenes of movies that there are 2,000 people that are escaping from zombies and stuff like that, right? It's a pretty challenging task to make it realistic, because you have to give design faces or get photos from Facebook and get sign so many agreements and stuff like that. But no, you can just generate them, right? Or in your video games, have you played one of those MMORPGs that there are what is it called? The people that are not actual players.
NPCs?
NPCs, right? And they look all the same, and it's kind of boring. Now you will be able to just like generate faces for them. And this is now a transition between the faces that is quite interesting. Again, none of these people are real people. Quite interesting. So another example, which I believe that is very interesting, is this example. This is also a generative model. So the previous example, just to make sure that I have talked about references, previous example was from NVIDIA. So this one is from Berkeley, UC Berkeley, north of here, right? Pretty interesting research, again, pretty recent. What it does is that this is another generative model. This model has shown, the researchers have shown daytime and nighttime videos of different places, okay, to the model. And then what they do is that they show only the daytime of San Francisco, and the model is creating without ever have seen the nighttime of that scenery. It hasn't seen the nighttime of that scenery. It will generate the night scene. So you give it the daytime of the scenery, and it will generate what would be the nighttime of that scenery, without ever seeing the nighttime of that scene. Pretty impressive, right? So again, it's a generative model. So the last one is, again, something interesting. Well, I have two examples, but I want to see if this link works. Hopefully, that's going to be better. And if
We're entering an era in which our enemies can make it look like
take a look
anyone
at
is
it.
saying anything at any point in time, even if they would never say those things. So, for instance, they
Oh,
could
you don't
have me
see
say
it. Oh. I was seeing that you guys are, doesn't look that you are interested. Okay, you don't see that. Okay, let me play it from the beginning.
We're entering an era in which our enemies can make it look like anyone is saying anything at any point in time, even if they would never say those things. So, for instance, they could have me say things like, I don't know, Killmonger was right, or Ben Carson is in the sunken place, or, how about this, simply, President Trump is a total and complete dipshit. Now, see, I would never say these things, at least not in a public address, but someone else would. Someone like Jordan Peele. This is a dangerous time.
Okay, let me pause here
Moving forward.
for a second. That video that you see on your left is actually generated. That's not a real video. So Obama never said those things, and that scene is not real. That is computer generated. And that's pretty impressive. And in fact, the way that it works is that it's a generative face model, and you can talk and have like emotions in someone else's face, and it will translate it to the person that you want. So while that person never had said those things, it seems that he has, right? So it's quite interesting and quite dangerous, as Obama, or better say, what was his name? I forgot. Is mentioning, right? So
We need to be more vigilant with what we trust from the internet. It's a time when we need to rely on trusted news sources. It may sound basic, but how we move forward in the age of information is going to be the difference between whether we survive or whether we become some kind of fucked up dystopia. Stay woke, bitches.
okay, so let's get back to work here. Okay. Okay, so I'm hoping that by now you are convinced that not only these deep learning methods are useful for doing some standard kind of tasks that we are doing every day, like driving or doing some medicine exams or stuff like that, but also they open up completely new directions to go. So it's quite an interesting and exciting area. I'm going to go quickly over how these things work, okay? I'm going to look at a very simple setup of the problem. And I'm not going to go over the detail because, of course, there's not going to be enough time to do that. But I will try to just roughly give you an idea of how these methods work. So these methods, there are a few main properties that all of these methods have. The first one is that they are hierarchical. So the way that they work is that they first extract some very basic, let's think about the vision problem for now, but they can be applied to sound, they can be applied to medical information, many other things, right? So I'm going to assume that the problem is a vision problem. So you have some input image. The first few, these things work in a hierarchical fashion. So the way that it works is that the basic layers will find very fundamental things and basic things in the image. For example, like edges and gradients and stuff like that. So these are the features that the first few layers will detect. Okay? Then, on top of that, other layers will combine these features together to create more meaningful and more abstract features. Okay? These are detectors. So, for example, if I use this filter or feature, what it's going to do, it's going to detect some edges with some angle like that. It will go over the image and it will see if that feature is presented anywhere in the image. Then the next layer will combine these lines and edges together. So for example, to eyes, nose, and stuff like that. And then it will go, each of these filters go over the image and it will try to detect where that feature is activated, right? So it does it in a hierarchical ordered fashion. And then again, more abstraction. If you go deeper into the network, you will get to the level that features are detecting faces. And not just faces, but faces of different people. Okay? So basically it says that if the person's eyes are that close to each other, it's John. If they're this close to each other, something like that, right? So there's a hierarchical way that these models are built. There's basically a bunch of layers that each layer is detecting different levels of abstraction of features in the input data. Okay? I know that if you haven't heard about them before, at this point it doesn't look that clarifying what I'm telling you, but I'm trying my best, right? So, and yeah, I really like this quote. The world is compositional, or there is a God. So the thing is that one of the main open questions in deep learning is that why does it even work? So many people believe that it's because the world around us, the physical world, is compositional. No one has a proof really for it, but it seems to be the case. Or at least it seems to be the case for the portion of the reality that we can comprehend. So, finally, after you do these detections and stuff, so you have some activations about all these features. The network will have a guess about the output. Okay, so maybe this is Alex, right? And then there is a loss function on top of it that will decide whether your answer was correct or not. If the answer was not correct, then it will send a feedback to the whole network. This feedback is using a process that is called backpropagation, which is pretty much like it's just taking the gradient. It's just chain rule. from calculus, Calc 3, that's pretty much it. So it's doing a stochastic gradient descent, which is a particular type of derivative. And it says that, okay, the answer is not correct, just update your weights, tune them in this direction. So it will, for every example that you give it, it will tune these parameters a little bit. Okay? So these guys are going to get better and better in detecting different things about your examples. And if you shoot it so many examples, after a while it gets very good in detecting different features in your data. Finally, it will get so good that it can do the task with high enough accuracy if you have enough data and if your model is created properly. So that's pretty much the deep learning in the simplest form. There are different versions of it. There are like a time-dependent version and recurrent neural nets, and there are like many different types. Recently, like the capsule model and others, but this is the simplest model. And in fact, this is the one that works the best so far, although being the simplest. So, going a little bit deeper into the mathematics and statistics of it, I will try to give you a few sentences about like the math point of view about the problem. So the problem, that quote is from a deep learning book by Bengio. What it is that assume that these are like data points of your data. These are samples of your data. Initially, it might look like these are discrete points in a very high dimensional space. But if you learn the correct features of these data points, you'll learn in most of the scenarios. In fact, it's in majority of the problems that we have seen so far in machine learning, it's like that. You learn that the data is just sitting on some regular, continuous thing that we, in mathematics, we call it a manifold. Okay? So a manifold is a space that it locally, when you zoom into every space part of it, it looks like Euclidean space. Okay? So example of a manifold is the surface of the planet Earth. When you're walking on Earth, it looks like it's a flat space, right? It's like 2D, XY plane, right? Locally. There are many more examples, and mathematically, these manifolds that are coming from the data are usually complex manifolds. Now, why does it make it any clearer that why these methods work? Think about it this way. If I know that there is a manifold, that all of the data, not just my samples, but all of the data is living in that lower dimensional manifold, what can I do? I can interpolate between the points within the manifold. Did you see those amazing generative models that were creating faces? That's basically based on this idea. So, so this is a very interesting point of view from a mathematical standpoint. Now, there are so many open problems in this direction, and this is very young. In fact, this point of view to deep learning and machine learning is a very new thing, and there are not many people who are still working on it. It's an exciting area. Yeah.
Roughly how new?
Around a few years, 3-4 years, right? So, I mean, 3-4 years in deep learning sounds like a lot, but note that when you go deeper into the science of it, then just 2 years, 3 years is not a long term, right? If you think about technology, it's changing every day, especially in deep learning. But if you think about the science of it, it's a lot more stable.
You mean like physics of it?
Not necessarily physics. I mean, I would say mathematics and statistics of it, right? To give you another example to make it a little bit more clear, again, so if you think about like for example my face, right? My face, if the continuity of the data is the important thing here. If you think about my face, of course, if I change my direction of my head or change the lighting a little bit, all the pixels that you're getting in your eye, all the light rays that you're getting in your eye are changed, right? When I change my face a little bit or change the lighting a little bit. However, these are changed in a continuous fashion. And this continuity is quite important because that gives you that surface that you can go around a given single point and find new points, or it also gives you predictive power. You will know a lot about the profile of this distribution, right? So that's quite interesting. And I think that, so this is a code quite interesting from Francio Charlotte. He's the guy behind Keras, if you know, that's one of the popular repositories in deep learning. And he says basically the whole deep learning can be kind of simplified, at least the supervised version of it, can be simplified as like a mapping between a space X to a space Y using a continuous geometric transformation. So it's basically like manifold embedding, the whole thing. Well, and maybe it's also interesting, doing this well is a game changer for essentially every industry, but it's also important to know that it's very far from human perception and human intelligence. Okay, so I want to end this portion with like just a bunch of open problems. For those of you who are interested to do research in this subject, there are so many different open problems. In fact, this subject is very young. If you think about it, it's a part of science. And when was the last time that you heard about a science that is just a few years old, right? I mean, if you think about like chemistry, mathematics itself, or whatever, they have been around for quite a long time, right? So there are so many open problems that you can work on. And that's very interesting and exciting. And there are so many low-hanging fruit in industry that you can work on. Like, I mean, really, I was challenging myself to how quickly I can start from just thinking from like scratch, how quickly I can come up with an idea that probably is interesting and no one has done it. And like I did it like 2 months ago, and it took me about half an hour. And the idea was that well, Google recently released their WaveNet, which is synthesizing human speaking, and you can give it a text and it will read the text for you, but it reads it in a way that you feel that a real person is reading it. Okay? Now, think about an application of it. So for example, one of the things that I always want to do is that I want to listen to podcasts, right? But sometimes these podcasts are not exactly the thing that I want to know. There are like internet articles that I want to know. But I mean, while I'm driving, at least, I cannot do that. Or even sometimes when I'm not driving and someone else is driving, just my eyes cannot really read while driving. But if there is like a auto-generated podcast, right? I mean, I'm just telling you that it's so easy to create new applications because it's so powerful and these methods are so new. Now, the theory of it is quite interesting too. So first of all, the rigorous theory of deep learning is still not known. So many open questions, and to put it frankly, we still don't know why these methods work. As simple as that. Okay? We have some ideas, but we don't know exactly. And there are some directions that seem to be maybe within the reach, but no one has done them yet. And things such as reasoning, long-term planning, sequential algorithmic manipulation, like the way that you write down an algorithm pretty much. These are the problems that we were not able to solve them using deep learning. And it sounds that maybe we should be able to do that in near future. So one thing that is quite interesting is that backprop, so Jeff Hinton himself was one of the main people who popularized the idea of backpropagation. And in a recent talk about a year ago, he basically said, my view is that throw it all away and start again. So maybe, and he has good reasons for that. It's not like, okay, I'm bored, but there are good reasons that are not, so it's going to take a long time to explain them. But it's an opportunity, because backprop is already working very good. And those, if you can find something that doesn't have inefficiencies of backprop, it's going to open up new directions. One thing that I personally believe that it's probably one of the most important paths in deep learning is a Bayesian approach to deep learning. I personally believe that the right approach to deep learning is Bayesian. And I think that's not just me. Yang Goodfellow, one of the very high-profile people in deep learning, also thinks that Bayesian is probably the way to go. So there are a lot of problems to solve in Bayesian. The problem is that Bayesian algorithms are usually very inefficient. So if someone can find a way to make them efficient, that's a very interesting thing to do. And finally, these two are very important, unsupervised and reinforced learning. Probably you have heard about the advances of like AlphaGo, that Google could beat the best Go player in the world and stuff like that. It's possible to do reinforced learning, but these methods are extremely inefficient. So you have to train them for such a long period of time for so many data samples. And we don't know why they are so inefficient. I mean, there are some, well, we know their structure and we know how they work, but one very interesting direction is to find a better way to train these models. And also unsupervised, which is probably like the holy grail of deep learning in general, or machine learning. You had a question?
You mentioned Bayesian methods are inefficient and they involve a lot of computation. So
right.
Is it because of the assumption that we make, the dependence between the events when we make our Bayesian model?
It's related to that, but it's mostly because if you look at the Bayesian formula for how you find the distribution, like the resulting distribution, is through a big number of integration. So generally calculating derivatives, which is like the backprop idea, is much more efficient. I mean, there's much more to it, but I'm trying to just like give you like one short answer. And generally, going over these integrations over such a high dimensional space is not a tractable thing. So you cannot really do it very efficiently. So these are the so many open questions there are in deep learning, and so let me talk quickly about entering the field. And I think we have to be a little bit quicker at this point. So let's talk about entering the field. Let me first make it clear that entering the field is not necessarily easy, as opposed to what you might have heard in like the YouTube channel of someone, right? And the reason is that there are a number of reasons. First of all, there are too many resources, right? There are online courses, there are these books, there are like articles, and so if you just search deep learning, it's everywhere nowadays, right? And it's quite hard to know which is the right direction to go, where to start, what is the best thing to read, right? So It's gonna make it's making it hard. Second thing is that the field is young and not mature, in a sense that you won't find a very clean, solid resource that starts from the beginning and get to a decent advanced point in the subject. We don't have such thing. The best resource that we have is just one textbook that was written by very well-known people called Deep Learning, right? And I believe that it was published just recently. It was on the internet for around maybe 2 years now, but officially it was published recently. It's pretty much like just the only textbook that we have on the subject, and even this textbook, I wouldn't call it a textbook. It's more like a bunch of papers put together. Okay? So the field is so young, make it very hard to continue. Also, it's multidisciplinary. You have to learn mathematics, you have to learn statistics, you have to learn programming. There's so many different things you have to learn. So it makes it very hard to navigate and to learn the minimal thing you require to continue, right? And if that's not bad enough, the field is changing very rapidly. So it's really hard to stay on top of things. So this whole thing makes it hard to navigate this field. I have a few suggestions for you, for those of you who want to enter the field. I don't think these are ultimate suggestions, but maybe there's a little bit of information. And my suggestion is that first decide where you want to be in the spectrum of deep learning. Deep learning is, as opposed to most of other branches of science and technology, has like a wide spectrum going from applications that are just like very down-to-earth applications, the applications like for your cell phone to take a selfie and put makeup on your face, right? Which might need a lot of work. I'm not saying that that's easy, but that's like a very real-world application. And it goes all the way to like the hardest mathematics and statistics theories. Okay? So there's like a spectrum of all different things. And you have to first decide of how much of application person you want to be and how much of research you want to be, right? So if you really want to go for like doing hardcore research and continue your PhD in a like top school or whatever, I would recommend that you start with the deep learning book, okay? And then find your way to the papers. That's if you don't have a mentor. If you do have a mentor, probably you can bypass that and go directly to papers. If you have someone can lead you. But if you don't have a leader, just go to the deep learning book and start from that and then try to find your way to the papers. That's for people who want to go very deep into the research path of deep learning. For people who want to have a little bit of both, maybe you want to start with like some Kaggle competitions or maybe hackathons, so you learn some basics and then get your hands dirty very quickly. Note that when I said to go over deep learning and like papers, you still need to do the implementations, otherwise you're not going to learn, right? I'm just saying that the focus is going to be on those papers. And if you want to really go hardcore for applications of it, probably you want to go with Coursera, Udacity. There are good courses that you can take, and they will teach you, they will actually teach you a little bit of theory too. They are not just dry out of all the theory, but they don't go very deep into the theory. They just teach you enough so that you know what you're doing, right? And then there are also a lot of channels on YouTube and blogs that you can follow. These are also could be interesting resources. So I think that the best idea on how to navigate is to first decide where you want to be in this spectrum, and then based on where you want to be, you can have a clean target. So maybe I want to just give you a few minutes to ask your questions, because maybe for some of you this is the subject that, for the ones who want to enter the deep learning. Is there any question?
The book you're talking about, is it the one by MIT by Fellow?
Yeah. Yeah.
You may not have the answer, but when it comes to Coursera, Udacity, etc., how seriously do employers take those certifications? Are they considered, compared to a degree, you know what I'm asking?
Right. I believe that they are like small pluses. You're not going to be able to just go over Coursera and get a certificate and then go work for, like, in Google DeepMind, right? But that being said, it's a good starting point. So you can learn a lot from those courses, and then you define your own project and create a hopefully popular repository, or maybe if you're very good in research, publish some paper, then you can get to like best places, right? But I don't think they are enough like on their own. They are not enough. Like the certificates don't matter that much. Try to learn from them, but that is pretty valuable. Okay, so let's switch gear, and I'm going to show you one simple example, toy example of implementation. As I told you, I'm not going to go over the detail of it, but I'm just going to show you the rough idea of the code and how you can build a model. It's mostly, these kind of things are hacky, in a sense that in the spectrum of applications to research, these kind of things are falling into the application side, right? And you don't need to know a lot of the theory to be able to do these things, okay? That being said, I believe that it's a trade-off. If you go very hardcore to application, these applications are quickly changing. So you have to be on top of everything all the time. If you go very hardcore to research, it's harder to get into it. But when you are in a good point in the research, then they're not changing that rapidly. So you can keep your knowledge for a longer time. So it's like a trade-off. Okay, so this is one simple question. You give an image to your model. That's the goal. We want to do something like that. You want to give an image to your model together with a question, and the model is supposed to answer your question. Okay, that's pretty cool, right? And it's a question and answer problem. Let me explain what is the setup of the model that can solve this problem. By solving, there are many different things that you are referring to when you are in deep learning. Because solving a problem really, the hidden thing in it is with what accuracy, right? You can solve every problem with every model. And in fact, a while ago, I was working with a friend of mine who we are working in a project on industry, and we were like pulling our hair off to make our model a little bit more accurate. And I was reading an article, and it was in a place that there are a lot of hackathons going on and stuff like that. And someone who was a friend of my colleague came in, and we were talking about what we're doing. And he said that, oh, that's nice. I think I can do that in like 1 or 2 days. And I was thinking in my head that we've been working on this for 8 months now. And we're not stupid. And also the paper that I was reading was a paper from MIT together with Amazon that was published a week ago exactly on the subject that we are working on. So even if we are stupid, it cannot be the case that like 3 people from Amazon and 2 profs from MIT, all of them are stupid, right? So what is going on here? At first, I got kind of pissed off. That was, what are you even saying? But then I realized that he is not he's not totally wrong. He can do it, in fact, in 2 days. But of course, with not a very high accuracy. And that's what we were shooting for, right? We wanted to get this model that is indistinguishable from like human performance. And if you want something at that level, then it's going to be very complicated. But if you want to just do something at the basic level, which is what I'm telling you right now for this problem, it's not that hard. I mean, as soon as you get familiar with the technology around it, like TensorFlow, PyTorch, blah, blah. So to solve this problem, you have, well, your input is made out of 2 parts, right? An input image and a question. You vectorize everything first. It's called embedding, and that's exactly the area that I'm doing research in, embedding. For the first one is an image. So you do a convolutional neural net, you pass it to a convolutional neural net, and you extract one of the hidden layers, one of the intermediate hidden layers as your representation of the data. Depending on what dimensionality you want and how much abstraction you want, you might go deeper into your network, right? So usually it's common that you train a CNN, a convolutional neural net, on something like an image net, right? And then you extract the weights and then you use this for embedding. So you embed your image using a CNN to an image vector. This will be a vector, for example, of 100 dimensions, that if you give it an image, it will give you back this 100-dimensional array of numbers. These numbers are indication of whether different abstract features are presented in your image or not. Okay, for example, is there a wheel in it? Is there a light bulb in it? Is there and if like 10 of them are light up, it means that there's a car in your image, something like that. Okay, so this is like the abstract representation of your data in a lower dimensional space. So for the question, you first break it into words, and then you turn these words also to vectors. It's called word-to-vec. It's a very interesting idea. In fact, it's pretty simple. It's one of those simple ideas that it works, right? And there's not enough time to go over it, but that's one of the things that I always like to explain to everyone because it's very simple, but it's still it works pretty nicely. So you turn these words and you extract a vector out of each of them. Now these vectors have the information, the semantical information of those words in them. So, for example, the relationship between the word queen and king is the same as semantic relationship between husband and woman, kind of. Like you can see it in those vectors. So you then embed the question using a word-to-vec method to a bunch of vectors. And then you feed it into a LSTM. LSTM is a way of working with a time series, right? So if you have a bunch of information or vectors that are related to each other in a timely fashion, so think about a question, right? The order of words matter in the question. If you change the order, for example, a statement turns into a question, right? So the order that they are combined together matters. So you feed it to a LSTM model, and then you extract out of that a vector for the whole question. So this is going to be a question vector, okay? So now you have a vector, image vector, that is representing the visual information in your input, and you have a question vector that represents the question of your input. You concatenate together, basically put them together in a higher dimensional space. Okay? Note that these spaces are all Euclidean spaces. Okay? And then on top of it, you put a classifier. So the classifier gets the information from these vectors and combine them into one condensed final thing. Okay? And it will give you back a word vector that then you can translate it into words. Okay? So it gives you back a vector and you translate it into words. And let me show you the code. This is the code of it. I'm not sure how much of it you can read, but the interesting thing about the code is that creating such a complex model using at least the technology that we have right now, for example, I'm using Keras and TensorFlow here, is not that hard and it's not very long. The whole model is just this. Think about it. So let me explain what is going on. At first, I'm importing all the libraries that I need, Keras and TensorFlow, blah. This is the part that I'm reading the image, right? Then I'm feeding that image. So this is CNN is the part that I'm creating that CNN model. I'm using some so ImageNet weight, so it's pre-trained on ImageNet, and I'm using the Inception V3, which is this particular structure for neural nets. It's a good structure. It's kind of standard. A lot of people use that. And then I feed in the image to the CNN, and I capture the output vector. Okay. For the question, I will first. That's the input. I will embed it using a Keras layer embedding. I need to prepare here a dictionary for all the words that are allowed in my questions. Okay, so that the whole problem needs a little bit of pre-processing and playing around with the data too. Of course, every machine learning problem needs that. And then I specify what is the dimensionality of the vector that I need out of the words. And then I feed it the question, and it returns to me the embedded words. So these are like vectors for the words. Then I feed them to an LSTM module. And I specify what is the dimensionality of the vector that I want out of it. Next step, what was the next step? Concatenate the two. I will concatenate them to a layer, and I will put one layer of dense network on top of it. For those of you who don't know what these things are like building blocks of deep learning. But yeah, so. And then finally a ReLU on top of it, activation on top of it, and I will extract a prediction. Now, then I will feed in the question, this couple of image and question together with the correct answer to the model, and I will train it on that. How do I train it? With just basically a stochastic gradient descent. This is I'm using an Adam optimizer. It's a standard method of optimization. Generally, all these methods are based on gradient descent, backpropagation. Okay, there are a few different modifications to them. And then I'm passing the loss to the gradient to be able to update my weights. After I do that for a big number of examples, then I can give a new example to my model and ask questions out of it. Okay? So this is going to be the kind of results that I'm getting. So I give it this image to my model, and I ask, what is the man doing? And the answer is, I mean, pretty accurate, playing tennis. And like, you can even ask things like, what is the color of his t-shirt? And it gives you blue correctly. And I wish that I had recorded a few of the wrong answers too, because some of them are funny, but I didn't. So maybe for some other time. Okay, everyone, thank you.
The dimensions that you wanted, like I remember it was 256 at first, and then it's like
right. So most of the dimensionality decisions is related to how much memory and how much computational power you have. If the dimensionality is higher, if it is not too high that the data is lost in the very big dimensionality, generally the rule of thumb is going to higher dimension will give you better result. But it means that you will need more computational power, need more memory and stuff like that. So you usually go with the lowest dimensionality that gives you a decent result. These kind of things are hyperparameter tuning, so you have to go over several different models, decide what is the best dimensionality.
Do they have to be power of 2?
No. There's nothing special about power of 2. You could go with any other value. It's just that computer scientists like powers of 2 better. That's it.
Are there only ones and zeros in the vectors? I'm just curious.
In the vectors inside the neuron, no. These are real value vectors. They can take any value, and even negative values. Any other question?
So, how well does this work with like words? So if you take in like an entire essay, could it reproduce just like BS essays?
Yeah. So if it can generate essays on its own using generative model. One thing that happened for current deep neural nets is that when you look at the generation of something like an essay, in a close neighborhood of every sentence, it makes sense. But when it's not capable. So their memories are very short term. Mm-hmm. So when you go to like a long passage, all of a sudden it kind of loses the connection to the beginning of it. It looks like if you just read it sentence by sentence and don't try to follow the logic of it, it makes sense. It seems like a person wrote it. But yeah, if you look at the whole, okay, so what was the story about, then it doesn't make sense.
So the follow-up to that is how close are we to understanding like context and language and like making it reproduce its own algorithms or anything of that sort?
Right. So that's one of the fundamental questions. So it's related to a broader question of abstraction. In your mind, even if you don't know anything about any language, you can think about, like, you can plan ahead in the future for long term, right? You can imagine what would happen if you were a billionaire, right? And what would you do? How would you, you can think about it without this being actually happening, right? This kind of long-term prediction of the future or stuff like that is, and the abstraction, and basically get an abstraction of this world and manipulate it. This is something that we were not able to successfully do it. And how close we are, I don't think anyone knows. But if we get to that level, basically we are not very far from human intelligence, right? Mm-hmm. But I personally, I don't have any proof for it. I believe that we're not very close. So we're still at least a few decades from that.
Right.
For the same problem, shouldn't RNNs work much better than CNNs, than what he was talking about? Because
right, yeah, of course. Yeah, but I was answering the question as a whole. It doesn't matter whether you use, like, the best methods that we have will not be able to reproduce like a level of abstraction that we want, right? So it doesn't matter whether you use like a CNN or recurrent network or whatever. It doesn't matter. We're still not there.
When it comes to synthesizing people's voices and actions, is there any sense of like an ethical committee that could guide?
That's definitely one of the concerns, especially recently in the AI community. And for example, with the example that I showed you, the Obama, it looks very realistic, right? If it was like 10 years ago, people could use that to sue Obama, right? And it seems that we're getting to the level that these kind of information that we can generate are so close to reality that there is this ethical question and also the question of reliability. How can we look at something and know that, okay, this is a legit thing, right? So these questions are very important questions. Or another related question is the question of like accidents in self-driving cars, for example, right? Who is the responsible?
Right.
So these questions are very important questions, and there are communities within the AI community that are trying to seriously consider these questions and answer these questions. For example, OpenAI was one of the companies that, first of all, they are doing great work in AI, and they started with this general idea of creating AI that is publicly available for everyone. So to make it at least like globally accessible, so that it's not within the hands of a few very strong companies or very rich people, right? So there are like ethical questions within the community of AI, and people are seriously considering those. I don't think we have like good answers for many of those questions, but people are working on it. Any other question?
Can you give some basic idea about how the embedding works, like how the vectorization of the image works?
Right. So let me go back here into the simplest example. So the embedding works something like this. When you go deeper into the network, so say that each of these will be a detector inside your network that detect different things, right? And when you give it an input, some of those neurons will be fired up. The amount that each of those neurons is fired up will be stored in a vector, right? It's a list of entries, and the amount that each of them is fired up is stored in a vector. That vector is called the embedding of the network at that level of abstraction.
So you explained a step in the model where you were going from words. So do we break each word in our question and then we make the vector of it?
Yeah, so you feed in each word to the word to vec, and then you feed that to LSTM. So basically, these are going to create vectors for you, and then the ordering of them is going to be captured by a LSTM layer. Any other question?
You mentioned you have to define your dictionary ahead of time.
Right.
That step. Is there anywhere, I know you're limited time, is there somewhere online I could dig into your pre-processing code a little bit more? And see,
yeah, I don't have it with me, but I can show you later. You're in one of my classes,
I'll send
right?
an email.
Sure,
Actually,
yeah.
no problem.
One last question. So for your hierarchical model, so if you have layers, do you order those layers? What does hierarchical mean in this scenario?
I'm not sure if I got you.
So hierarchical.
A little bit louder.
I know you explained the layers.
Right.
I follow that concept. So in the deep learning or the neural networks, we have the additional layers,
Right.
and we feed our errors to make this process more and more efficient for our prediction purposes. But what does hierarchical? I haven't studied hierarchical in this.
Oh, right. The hierarchy, it's just referring to the fact that each layer is connected to the previous layer in a combinational fashion, in a way that it can combine the previous features into a new feature. Okay, so each new feature is a combination of previous features. It's kind of like a more abstraction of the previous layer. So that's why it's called hierarchical model. And deep is referring exactly to that you have several different levels of abstraction.
So there is a dependence between each layer?
Yeah, each layer is getting the information from previous layer. Anything else? Okay, guys, thank you. I will be here if you have more questions or whatever.